Hi, I'm Øystein Runde, and this is Wunderdog, the podcast that is obsessed with getting humanity from one planet to many. Today's guest has worked on the Search for Extraterrestrial Intelligence Institute, SETI, and she currently works at NASA JPL, which is the coolest part of NASA, literal rocket science. She is a brilliant researcher. She's done a lot of amazing stuff, and you just need to meet her.
Thank you. It's great to be here. My name is Dr. Cynthia Phillips. I'm a planetary geologist and I work at the NASA Jet Propulsion Laboratory in Pasadena, California.
Your mission is currently Europa Clipper, isn't it?
Yeah, I work on the Europa Clipper mission, which is a mission that NASA is currently working on that'll be launched in just a few years now to explore Jupiter's moon, Europa.
What's your position in this project?
I'm a project staff scientist, which means that I kind of do whatever needs to be done. And I'm also the science communications lead for the mission, which means that I get to talk to people and help shape the story of Europa.
Okay, so let's begin. What is Europa?
So Europa is a moon of Jupiter. It's about the same size as Earth's moon, but it looks very different. The surface of Europa is covered with a layer of ice. And we think this ice layer is between 30 kilometers thick, maybe a little more, maybe a little bit less in some places. But below that ice layer is a giant layer of liquid water, a subsurface ocean. And we think that that ocean contains more water than all of Earth's oceans combined.
All of Earth's oceans, and that's just the liquid water.
Yes, yes, we think that there's a layer at the surface of Europa. So Europa's interior is rocky, and then it could have a metallic core in the middle. But on top of that rocky layer, there's a layer of a combination of liquid water and frozen water ice that's about 100 kilometers thick. And so one of the big questions that Europa Clipper is going to try to address is how much of that ice layer is frozen ice and how much is liquid water.
How do we know what's in the middle of Europa?
We have measurements that were taken by the Galileo spacecraft. And so this was back in the 1990s. The Galileo spacecraft orbited Jupiter, and it had multiple close flybys of Europa and of the other large Galilean satellites, so Io, Ganymede, Callisto. And in the observations of Europa, we were able to measure Europa's gravitational field. And these gravity measurements basically can give you an idea of the density of Europa's interior and also the layered structure. So those measurements told us that there is a higher density solid interior of Europa, but then at the surface, there's a layer, and this is where that 100 kilometers thick number comes from. We can tell from these measurements that there's a layer at the surface, 100 kilometers thick, that has the density of water. The problem is that those measurements were not sophisticated enough to tell us how much of that water layer was frozen ice and how much was liquid water.
But we know there is some liquid water in there.
Yeah, and we know that there is, well, we are almost entirely sure, right? I'm a scientist, and so I'm not going to be able to say that there absolutely is an ocean there until we go there and directly detect it. But the evidence that we have from the gravity measurements, but also from other measurements that were taken by the Galileo spacecraft, tells us that really the only plausible structure for Europa has a thick ocean layer. And that comes from the magnetic field results. And so this is another instrument that was on the Galileo spacecraft. Europa doesn't have its own intrinsic magnetic field. That means that Europa doesn't generate its own magnetic signature. But as it orbits around Jupiter, Jupiter has a really strong magnetic field. It's a huge planet, the biggest one in the solar system, and its magnetic field is very strong. And so as Europa orbits Jupiter, it moves in and out of Jupiter's magnetic field. And the Galileo spacecraft was able to measure a response from Europa. And this wasn't expected. So we knew that since Europa didn't have its own magnetic field, we didn't expect to see much from Europa as we studied it, as it moved in and out of Jupiter's field. But in fact, what we saw was what was called an induced field. An induced field, for those who have taken high school physics, is basically when you have a conductor that moves through a magnetic field, you get an induced field that's, at a particular sort of opposite direction from the direction of the magnetic field that it's moving through. And so what this tells us is that there had to be a global conducting layer on Europa near the surface. When you combine it with those gravity results, really the only thing that makes sense is a layer of salty water. It turns out that salt water, like Earth's ocean water, is a very good conductor. And so what's happening is that as Europa moves around Jupiter, there's no atmosphere on Europa. So we know that the surface, it's not going to have liquid water anywhere near the surface, because if any liquid was exposed on the surface, it would just boil and freeze as it was exposed to the vacuum of space and the temperatures that are like 100 Kelvin. So really, really, really freezing out there. But below this surface ice layer, there's got to be this global conducting salty ocean layer. And it turns out that you basically don't even need a super salty layer. Salt water that's about as salty as Earth's oceans, or even a bit less, could explain the results that we saw from these magnetic field measurements.
Where does the salt come from? From the rocks?
Yeah, so salts are a pretty common component that we find in rocks and meteorites, in sort of like the building blocks of the solar system. So it's not too surprising if you have a liquid layer that's in contact with a rock layer at the bottom. It's not too surprising that the liquid could kind of dissolve some of those salts out of the rock layer, and it could kind of become a salty ocean layer.
When you say the surface of Europa, it feels like you mean the rocky surface.
Well, when I say this, so there's the icy surface at the top. So the surface of Europa, what's exposed to space, is this ice layer. And then below the ice layer, you have this ice water interface. So at the bottom of the ice layer, the top of the ocean. And then at the bottom of the ocean, you have this water rock interface. And so at the bottom of the ocean, the top of the rock layer, that's where this sort of interactions could take place, where some of the water could circulate through the rock and it could dissolve various materials like those salts.
Is it Europa we see behind you in your Zoom call background?
Yeah, yeah. So we don't actually know what the surface of Europa would look like from the surface. We've never landed on Europa. And the Europa Clipper spacecraft that I'm working on, it's not going to land on Europa either. But we have a few pictures that were taken at high resolution. And so, yeah, I have an artist's conception behind me of what it might look like to stand on the surface of Europa.
So this is about how bumpy it's supposed to be. I heard that Europa is the smoothest surface in the solar system.
Um, it's hard to say, right? We have images that were taken again by the Galileo spacecraft. That's really the only source of high resolution data that we have for Europa. There were a couple of flybys in the late 1970s, early 1980s by the Voyager spacecraft as they just flew through the solar system. They got us a few pictures of Europa. And then the Galileo spacecraft was able to take some images. But unfortunately, Galileo was hampered by its high gain antenna, which didn't deploy correctly. And so the number of pictures that the Galileo spacecraft could send back from the whole Jupiter system was very limited. And so we do have some images. We have one picture at a resolution of 6 meters per pixel. That's the single highest resolution picture we have of Europa, but it's one picture, okay? And then we have the rest of the strip is at about 12 meters per pixel. And then we have other images that are at, 20, 30, 100 meters per pixel. But none of those pictures, even our single highest resolution picture, none of those are good enough to really tell us the details of the small scale topography of Europa's surface. So we can make guesses based on other places we've seen and based on what we know about, the physics of ice, but we're not really going to know what Europa's surface looks like until we go there, and especially until we go there and land on it.
When are we going to land on it?
So I'm also working on what's called a mission concept. And this is, so behind me, I have a picture of what Europa lander might look like. So the Europa lander mission concept, it's a mission where basically it would be a follow-up to Europa Clipper. It would use the pictures and the other data taken by Europa Clipper to characterize the surface of Europa and choose a landing site. And then the Europa lander mission would go to that location, it would land on the surface, and it would actually be able to take, so the in situ pictures. So the pictures like the one behind me, I want a real picture of what would it really look like on Europa's surface, right? That's what I've been waiting for practically for my entire scientific career, is that one picture when we land. But in addition to pictures, there's also lots of amazing sampling that you can do from the surface. So this wouldn't be a rover. It wouldn't be something that would drive around on the surface. There's no atmosphere, so you can't fly around like the upcoming Dragonfly mission to Titan will be able to do. It would just be a simple lander, but it would land on the surface and it would have a drill or a scoop, and it basically would be able to, or a saw kind of, it would be able to dig about 10 centimeters, maybe more, below the surface of Europa, scoop up some samples and bring those on board the spacecraft for analysis. And the reason that we really want to do that analysis is that Europa, we think, could be one of the best places in the solar system to look for signs of life beyond the Earth. And so by landing on the surface of Europa, we'd be able to make a direct search for biosignatures. So biosignatures are basically chemical signs of life. So we're not expecting there to be fish flopping around on the surface of Europa, although, if there are, I'm not going to be disappointed, right? I'm going to be pretty happy to see a picture of a fish, but we don't think that there's any sort of macroscopic organisms that could make it to the surface. And actually, it's unlikely that large scale, fish or anything like that could exist in Europa's ocean. But we think that it's very possible that microscopic life, microbes, little single-celled organisms, those could exist in the ocean. And so by landing on the surface, that's really our first step in looking for life in Europa's ocean. We would scoop up that material, we'd bring it on board the spacecraft, and we'd basically look for anything, any kind of signs of life. And there'd be a suite of instruments on the spacecraft that would be able to measure, to look at the material from Europa's surface with like a microscope and other chemical analysis instruments, to look for signs of life.
But the 10 centimeters into the ice of the surface, that's going to be radiated by Jupiter's radiation. That's going to be like...
Right. So yeah. So basically, the first mission that lands on the surface of Europa, it's not going to be able to go anywhere near the actual ocean, right? Because that would require drilling through, 10, 20, 30 kilometers of ice. That's something we haven't even done on Earth before. So to think about doing that on somewhere like a moon of Jupiter, it's sort of the end game, right? Everyone wants to get down into that ocean with a little submarine and go, swim around and look for life, right? That's what I want to do too. But that's not going to be the first mission that we send to Europa's surface. So the 10 centimeter depth, yeah. So the reason that depth was chosen is that the surface of Europa, it's irradiated. So the radiation processing of Europa's surface is just crazy. So it's that same result of Jupiter's really strong magnetic field. You get these charged particles that are just accelerated and they slam into Europa's surface. So if a human was standing on Europa's surface, you can only live for a few hours before you get a lethal dose of radiation, basically. And so even our Europa lander mission is going to get irradiated. And it can only survive on the surface, even with like serious shielding around the scientific instruments. It can probably survive for about a month, maybe a bit more, before the radiation really starts degrading its electronics to the point that it's not able to function anymore. So it's going to have to be a quick mission. So fortunately, ice is a pretty good protector. And so it shields the subsurface from the effects of radiation. And so we have theoretical models that suggest that while the very top, surface of Europa is very, very strongly irradiated, we think that once you get down about 10 centimeters, maybe more, maybe we'll have to go more like 20 or 30 centimeters. But once you get down not that far below the very top surface layer, you can get into material that is protected from the surface irradiation. And so it's that material, that more pristine material, that we want to sample.
Yeah, my Norwegian JPL friend Tom, he wrote a paper in Nature
Yeah.
how 20 centimeters will be enough to shield.
Yeah, yeah. Tom is one of the ones who's working with us on this, and he's great. And his numbers are really essential as we start thinking about just how deep you would have to dig below the surface to get to this material that's been protected.
How many people are there in your group?
Um, there's we're a mission concept. So what that means is that we're not a real mission yet. Europa Clipper, it's been approved by NASA, it has funding, and it's going. And there's hundreds of people who are working on Europa Clipper. For Europa Lander, we're basically doing all of the groundwork so that hopefully NASA will pick us, my fingers are crossed, will pick us and we'll get to go. And so there's about, there certainly are dozens of people working on it, mostly on the engineering side. I would say that the core science team is about, 12, 15 people, something like that. And we're all doing other roles as well. So for example, I work on both Europa Lander and on Europa Clipper.
And you were a big part of developing both these projects. I saw your name from a very early stage.
Yeah, I was fortunate enough to get to work with the Galileo spacecraft team, the camera team, back when I was in graduate school, and I just fell in love with Europa. Europa is, my favorite place in the solar system, and so I've been working for the last 20 years to try to get the next mission back to see Europa again. I used to joke that, oh yeah, I want to see Europa again before I retire. And now 20 years later, it's not so much of a joke. But fortunately, the Europa Clipper mission, it's well funded, it's well underway. We'll be able to launch in the next, probably the middle of this decade. And we'll finally get to see some more close-up pictures of Europa's surface. The Europa Lander mission is going to take a bit longer, obviously, but we're hoping that if we can get the go-ahead to start this mission, basically, if we can be working on building the Europa Lander mission while the Europa Clipper mission is kind of underway on its journey to Europa, then it'll be ready as a follow-up. Because I imagine that Europa Clipper is going to find all sorts of amazing things on Europa, and we're going to want to have a follow-up mission that's ready to go to follow up on those.
Does Europa have geyser activity or like some volcanic action like Enceladus has?
So there's been speculation, and there's been sort of there's been some evidence, but it's very, very difficult. So on Enceladus, the Cassini spacecraft was able to detect these giant, geysers of material being thrown off of Enceladus's surface. And Enceladus is this little tiny moon of Saturn. It's much smaller than Europa. And so the gravity of Enceladus is very small. And so if you have these sort of geyser, these venting events where some material is being ejected from the subsurface off the surface, because the gravity of Enceladus is so small, you get these giant plumes. So if we had similar eruptions taking place on Europa, people have proposed this, since back in the Galileo days. There's been theoretical models that, yeah, if you have a subsurface ocean, you have this ice layer on top, maybe you could have some kind of pressurized cracks or something that could bring some of that water closer to the surface, and then you could have maybe some kind of eruption. So people have certainly thought about plumes. We looked for them during the Galileo mission. That's one of the things I helped do, was design observations to look for potential plumes, and we didn't find any during Galileo. So in the 20 years since the end of the Galileo mission, we've been able to observe Europa with other instruments, so with Hubble Space Telescope, for example. And with Hubble, even though you're observing it from here, in Earth orbit, so you're much, much further away than we were with the Galileo spacecraft, Hubble has just an exquisite range of instruments on it. And so there have been a number of observations that sort of have provided intriguing potentials for plumes on Europa. And over the last couple years, we've seen a couple of these observations taken by Hubble and also by other Earth-based telescopes as well. And so they've given the potential for, they think that they've detected something sort of off the limb of Europa. The caveat with all of these observations is that they're really very close to the limit of detection. You're sort of pushing Hubble or these other telescopes as much as you can to try to squeeze out data for this small moon of Jupiter that's very far away from the Earth. And so the detections are all kind of like just a pixel or two, and they're sort of just above the background, right? So you can kind of believe them, but the thing is that you don't always see them, right? You don't always see these pixels that are said to be plumes, and that could just be that the plumes are variable, right? That they're not always erupting, or it could be that you just happen to get a hit of radiation noise or something that was right near the limb of Europa. So I would say that the evidence that we have so far, certainly theoretically, there could be plumes on Europa. And the observations that we have from this telescopic data, it's intriguing, right? But I would say it falls far below the level of what I would call definitive proof. Again, speaking as a scientist, right? I would love for there to be plumes on Europa. I would love for Europa to be geologically active, but I really have to have an overabundance of evidence before I would believe it.
But is the core, the metal rocky core, is that volcanically active? Is that, I mean, I hear it's been heated up by the friction or from the gravity of Jupiter. Is that true?
Yeah, so the whole reason why it's even possible to have a liquid ocean out on Europa, right? So Europa, it's 5 times further away from the sun than we are here on Earth, right? So the sun is like a bright star in the sky. So it gets very little heating from the sun. And so really early on, people thought, well, these are just going to be frozen rocks, right? There's not going to be anything interesting going on these moons out in the outer solar system. And what we found with the very first flyby, the Voyager spacecraft, and it was even predicted theoretically before Voyager went by the Jupiter system, was that you have what's called a resonance. And so basically there's these 4 large Galilean satellites. There's Io, Europa, Ganymede, and Callisto. And that's in order from closeness to Jupiter. So basically the 3 innermost, so Io, Europa, and Ganymede, are in what's called a resonance. And so that's this sort of mathematically elegant system where basically every time Ganymede goes around Jupiter once, Europa goes around twice, and Io goes around 4 times. And so what that means is that they line up in their orbits. And so what happens just over time, just due to physics, is that if you just had one moon that was orbiting a planet, over time, its orbit would tend to become circular, just because if there are any kind of wobbles in that orbit, then if it was a little further, basically the energy, the way that the energy works is that it would tend to become circular. Over time, it wouldn't wobble closer and further away. And so that's called a circular orbit, has what's called very low eccentricity, or 0 eccentricity if it was a perfect circle. So what happens, because there's these 3 large satellites, so Io, Europa, and Ganymede, is that you get what's called a forced eccentricity. And that's because of the numerical basically alignment of these orbits. That means that Io and Europa are at the same place in their orbit each time that they pass each other. And then same thing with Europa and Ganymede. So they basically tug on each other. They give this little tug, and they create this forced eccentricity, which means that the orbits are non-circular. Okay, so that's important because the distance then from, say, Europa and Jupiter changes over the course of Europa's orbit, which is about 3.5 days. So sometimes Europa's closer to Jupiter, sometimes it's further away from Jupiter. And that matters because, again, Jupiter's gigantic, right? It has more mass than basically all the other objects in the solar system combined. And so its gravitational pull, its gravity is hugely strong. And so sometimes Europa is closer to Jupiter. That means that Jupiter tugs on Europa more. It raises what's called a tidal bulge on Europa. And then sometimes Europa is further away. So the gravity is less and that bulge goes down. And so basically over the course of its orbit, Europa gets stretched and pulled and squeezed as its surface basically goes up and down due to Jupiter's gravity. And so it's the combination of the resonance from Io, Europa, and Ganymede, plus the strong gravity of Jupiter that creates what's called tidal flexing or tidal heating. It's kind of like if you take a rubber ball and you start squeezing it a bunch, that ball is going to get kind of squishy and it'll get warmer. And that's because you're putting energy into the ball. And so when the first spacecraft, when the Voyager spacecraft flew past Io in the late 1970s, we were able to see volcanoes erupting on Io. And again, this was actually predicted theoretically even before the Voyager spacecraft got there. So Io is basically, it's the closest one in to Jupiter. It's the most volcanically active body in our solar system. And basically that's because of all of this heat. So Io's orbit, its eccentric orbit, so its distance from Jupiter keeps changing. It keeps getting tidally heated. And basically if Io ever had any water or ice on it, it's been just blown off long ago. So Io is this volcanic, it's this surface covered with melted rock and molten sulfur, and it's just this crazy world. So then if you go out, Europa is the next one. So Europa has enough tidal heating to keep a liquid ocean liquid over the age of the solar system. So basically, we think that this resonance has been there for billions of years because it's a very stable configuration, basically. Once the satellites formed and they kind of got into this configuration, it's very stable. It would be very difficult for them to move out of this configuration unless, say, a giant asteroid or something came in and whacked one of them out of position. That's really what it would take to get them out of this resonance. So basically, Europa has enough heating to keep this liquid water liquid, to keep this ocean liquid. And then Ganymede, which is further out, we think also has an ocean, but it has less of the heating, right? So it's further away from Jupiter. It's bigger as well. So we think there's an ocean on Ganymede, but it's under, say, hundreds of kilometers of ice. So it's much further away from the surface. And the ocean on Ganymede too, rather than being on top of a rocky interior, Ganymede has a lot more ice in it than Europa does. And so probably on Ganymede, you have, say, hundreds of kilometers of ice at the surface, then you have a liquid water ocean layer, but then there's more ice underneath that. And so that has implications when we start thinking about the like the salt in Europa's ocean, for example, that comes perhaps, and also the other interactions that could take place at the bottom of an ocean layer, sort of an ocean rock interface, like at Earth's seafloors.
So you got, just like on Earth, these volcanic areas where there's life that's never seen the sun.
Right. And so again, this is all theory, right? So it's theoretically possible that on Europa, we could have, say, hydrothermal systems, right? So all of that tidal heating, that tidal energy, um, we still don't know exactly where that energy is placed. So does that energy mostly go to, say, the ice shell, so the top of the ocean, the ice water interface, or is more of that energy placed in the interior, in the rocky interior of Europa? If more of the energy goes there, then yeah, it's quite possible that you could have subsurface, basically volcanism. You could have these hydrothermal vents that are bringing heat and nutrients to the bottom of Europa's ocean. And if that's the case, then yeah, they could be amazing analogs to the hydrothermal systems at the bottoms of Earth's ocean. Right. And so one of the things that we've discovered, again, just in the last 25 years or so, is that the bottom of Earth's ocean, which once was thought to just be this dead kind of zone, there's abundant life that lives at these hydrothermal systems, at these black smokers and vents. As we've gotten down there with submersibles, we've been able to see that life there, and it's teeming with life. Right. It's not just a few cells, it's these tube worms and fish and just all these amazing things that exist at the bottom of Earth's ocean. And yeah, like you said, they're mostly independent from sunlight. One difference at the bottom of on Earth's hydrothermal systems is that it turns out that a lot of the life there does actually require materials that are created at the surface of the ocean and basically kind of like percolate down through the ocean layer. So it's this rain of sort of like, food that kind of falls down through the ocean to the bottom. And so a lot of the life at the seafloor on Earth does actually require some of those nutrients that originally were made at the surface. And so on Europa, photosynthesis is not going to be an option, right? You're not going to have any life that's kind of sticking its head out of the ice layer to try to get some of that sunlight. Because the sunlight is so weak out at Europa, but also because it would just get fried by radiation far before it could do any useful photosynthesis. So in Europa, if there is life in the ocean layer, it's going to have to be completely independent from sunlight.
So that means it cannot be as complex as the black smoker life on Earth, because it'll have less complex amino acids and less complex proteins to eat, basically.
That's our guess, yeah. There are folks who have done sort of an analysis of the total amount of energy available for life on somewhere like Europa. And so it does look like there's enough energy, there's enough kind of, redox gradients and chemistry and sort of the things you need for life to support sort of basic single-celled life. But unfortunately, we do think that multicellular life, so, whales or giant squids or fish or anything like that, it's probably very unlikely to exist on Europa, which is unfortunate.
Yeah, it's simply not, it's enough water and there's enough oxygen and salts, but it's just not enough complex proteins.
Right. And again, that's what we think, right? I would love to be proved wrong. If we land on Europa's surface and we, find a crack where there's a giant squid that's waving at us, I would just be so excited. But again, speaking as a scientist, I think it's very unlikely that we would have, kind of higher order, more complex life forms on Europa.
You say that Europa is stretched like a rubber ball all the time. Wouldn't that make cracks in the ice?
Right, it does. And so Europa's surface it's covered with cracks. And that was one of our first hints when the Voyager spacecraft flew by, when we saw the surface for the first time close up. We saw that it was covered with these long linear features, these cracks and these ridges and these places where the surface has just been broken up. And with the Galileo spacecraft, we were able to map those out in much more detail. And we see, there's these long linear cracks that are, about a couple kilometers wide and maybe a few hundred meters tall, but they stretch for thousands of kilometers across the surface. And there's other regions that we call chaos terrain that kind of look like icebergs. And they're basically places where the surface has been broken up. So the pre-existing surface crust that's all full of ridges has been broken up, and these blocks have basically rotated and translated and sometimes even tilted. And then they're sort of refrozen into their new positions. And so all of these cracks and these ridges and then these kind of icebergs, I call them icebergs, but they're orders of magnitude bigger than any icebergs that we see on Earth. So they're huge. But all of these features, people have proposed, there's a lot of very intriguing modeling you can do to try to figure out how these features form on Europa's surface. And again, we know there's this ocean layer underneath, and this interesting geology was actually one of kind of the indirect signs of evidence that pointed us toward there being an ocean. But the problem is that since liquid water is actually denser than solid ice, so it's actually, you have this buoyancy problem. It's actually very hard to get liquid anywhere near the surface of Europa, because the ice just wants to float on top of it. And so a lot of the models, like for example, these icebergs, right? So, you think, oh, well, you see icebergs, that must just mean that, there's water close to the surface and these blocks were just floating around on it. And then they just kind of got stuck and frozen in their new places. But the problem with that is that it's very, very difficult to get enough liquid anywhere close to the surface for anything like that to happen. So it's really a puzzle. There's people have been trying to figure out how these features form for 20 years now since we saw the Galileo data. And so that's part of why it's going to be really exciting to be able to see the new high resolution pictures that we're going to take with Europa Clipper and hopefully finally solve some of these puzzles. let me just tell you one more thing about Europa. Okay, and so this is I want to tell you a story, and this is the story of why I think Europa and not Mars is the best place to look for life beyond the Earth. And so basically, there's a lot of we call Martians, basically, that's what we call the people who study Mars. Okay, so there's a lot of people who study Mars who think that Mars is the best place to look for life in the solar system. And NASA has spent a lot of time and effort, sending rovers to drive around to Mars and, look for signs of ancient water. And we're working on this whole Mars sample return project right now that would actually bring some samples from the surface of Mars back to Earth. And so that's exciting, right? There's nothing wrong with Mars. But the thing is, when you think about life on Mars, all of these searches for life, you're basically talking about fossilized, old dead fossil life. Because today, even if Mars had a period back in its geologic history, millions and millions of years ago, when the surface was warmer and wet and when there might have been liquid at the surface, today Mars is old and cold and dry. And so there's really no one saying that life could survive today on the surface of Mars, maybe somewhere in the subsurface, but not on the surface. So if you compare the search for life on Mars to the search for life in Europa, when we think about life on Europa, we're talking about an extant ecosystem. So life that could be surviving and thriving in Europa's ocean today, right? So if we want to study a place where there could be life today in our own solar system, Europa is the best place to go. But there's another reason why Europa is an even better place to go than Mars, and that's this. So basically, Mars is close to Earth, right? And so we know that Mars and Earth, we know that Mars and Earth have actually exchanged material. So we've found meteorites on the surface of Earth that we can prove come from Mars. And that's because their composition and the trapped sort of gases and other materials exactly match the measurements that we took when we landed on Mars. So we know that it's possible for rocks from Mars to land on the Earth. And so that means it's also possible for rocks from Earth to land on Mars. Rocks can go both ways. And some of the studies of how material can be exchanged between these two planets show that depending on what kind of event ejected that material, so it probably was a big impactor, so a big asteroid or something that hit the surface of Mars, it threw off some material. Some of that material went into space and then eventually landed on the Earth. So some of the models of those impact events show that there are trajectories where this material could come, just over a few thousand years, so very quickly could come from Mars to the Earth. And that's long enough for, if there were, say, like spores or some kind of signs of life in the interior of one of these rocks, they could actually survive the trip. So it's not crazy talk, right, to say that life could have started on Mars and then been transported to the Earth. Or conversely, life from Earth could have hitched a ride on one of these meteorites and made it to Mars. So, we sometimes say that Mars and Earth have been swapping spit, for 4 billion years, right? They've been throwing rocks back and forth at each other. There could have been anything hitching a ride on those rocks. And so even if we do find life on Mars, and don't get me wrong, I would be very excited to find life on Mars, right? That would be amazing. But there's no guarantee that that life on Mars would mean that there is an independent origin of life, right? It could just mean that, we're all Martians, right? Life began on Mars, it made its way and it seeded the Earth from Mars, or vice versa, right? But it's not necessarily a totally independent origin of life. Okay, so then we think about Europa. So Europa is much further away. It's out in the Jupiter system. And so it's basically dynamically very, very implausible. So, almost impossible for any material to be transported between Earth and Europa, or between Europa and Earth. And that's basically because it's much further away, but also because if any material from Earth actually made it out to the Jupiter system, Jupiter is so gigantic that it's going to crash into Jupiter, right? The chances are vanishingly small that any of that material would actually make it to Europa. And then vice versa, if any material actually made it off of Europa, it's just going to get sucked into Jupiter, right? The chances of it being lost from the Jupiter system are vanishingly small. So what that means is that it's like there's an isolation barrier between Earth and Europa. So if we find life on Europa, that means that it's an independent origin of life. Okay, that life it started completely independently of any life here on Earth. And that is a profound concept, because what that would mean is that in our solar system, our dinky little solar system that's in an unfashionable arm of a spiral galaxy, right? That in our solar system, life started not just once, but twice. And if life could start twice here, basically in the two places that were the most habitable, if life actually started independently in both those places, then you look up at the sky. And so the other revolution we've had over the last 20, 25 years has been, we now know that basically almost every star you look at in the sky has planets around it. There's these huge abundance of exoplanet systems, right? And so as you look up in the sky, as you look at all of those stars, as you think about all the planets around those star systems, if life could start not just once, but twice in our little dinky, unremarkable solar system, life has got to be abundant, right? It's got to be on so many of those other planets that are surrounding other star systems. And so to me, that right there would completely reshape our idea of our place in the universe. And so, discovering life on somewhere like Europa, it would just be a profound, civilization scale discovery about not just our own solar system, but about, our future and our place and how we fit into the galaxy. And so, I get chills every time I think about it.
And you're gonna be smack in the middle of this civilization scale discovery, aren't you?
This is why we need to land on Europa. This is why we need to get into Europa's ocean, because there could be life there. And yeah, and it would be so profound to find that life.
And there's also, I've seen these models that Tom Nordheim are working on this, when you make Christmas cookies, this roller, it's like a rolling pin, and it's supposed to melt its way through. It's called brûlée.
Yeah. We've been looking into, how you would get into that ocean. Because the Europa Clipper mission is going to observe Europa from orbit. It's actually in orbit around Jupiter with multiple close flybys, just because if you're actually in orbit around Europa, you start building up that radiation and you can only last for like a month in orbit. So these multiple close flybys will give us great remote sensing data of Europa's surface. But yeah, if we really want to explore Europa, we need to land. And then after we land, after we get information that sort of that in situ ground truth for all this remote sensing data, we will be able to study the subsurface much better using seismic instruments from the surface. That'll lay the groundwork for eventually a mission that goes through Europa's ice layer. And there's a couple different ways of doing that. One of them is a drill, but probably what makes a lot more sense, given that Europa's surface is made out of ice, not rock, is you can melt it. And so Tom and I are also working on basically a mission that would go into Europa's subsurface with a melt probe. So the idea is that you bring a heat source, and that heat source is probably going to need to be nuclear powered, just because that's that's the only thing we have that has enough energy density in a small package to be able to get through tens of kilometers of ice. But you bring a melt probe with you, and you basically melt your way down through the ice layer, and it could take years. But basically, you would do that, and then eventually you would get to the bottom of the ice layer into the ocean. And then you could deploy a little submarine or something like that that could go around and take pictures. So yeah, so this is much further off in the future than landing on the surface. Today, if someone gave me a gigantic bucket of money, we could start building this Europa lander mission right now. We have the technology, we know how to do it, it's ready to go. But for a melt probe or a subsurface mission, we're still in the early stages of figuring out how to do it, figuring out the technology. And so there's definitely going to be work to go on that, that we'll need to study and understand and then test out on some of Earth's terrestrial ice sheets to see how this kind of technology works before we can send it to Europa. But that's really the dream. The dream is to get into that ocean.
You said Tom and I. Is it just you two?
Oh no, yeah. So this is another sort of mission concept. It's not just me and Tom, but there's another group of people who are working on various missions, and not just at JPL. There's other places that are working on melt probes, but there's a particular sort of mission concept study that Tom and I are both part of at JPL that is looking at these sort of melt probes.
And what's the name of this project?
This is called PRIME, and this is just it's an acronym. I forget what it stands for. But yeah, it's basically it's another proposal. So we're waiting to see if we get some funding to continue with this.
You like funding. When I hear funding, I think about Yuri Milner.
Yeah.
The guy who gave Philip Lubin's project $100 million for
Yep.
breakthrough store shots. I don't know if you heard my other episodes, but I have an hour long interview with Philip about the breakthrough store shot, the giant laser.
I haven't heard that one, but yeah, I've been at some of these one or two of the sort of the breakthrough conferences that Milner has hosted.
Are they interested in your project?
Yeah, I know. I think that I know that Milner was looking for kind of an outer solar system project, and I think that my guess is that he's going more in the direction of something like Enceladus than Europa. But yeah, I don't know anything. I don't know anything for sure. If Yuri, if you're listening to this, I would very gladly accept any buckets of money you might happen to send in the direction of Europa exploration.
What's the most crazy ideas you have that you can talk about in public as a JPL NASA person?
Well, tunneling below the ice of Europa to get into its ocean is pretty crazy. So that's really what I what I spend a lot of time thinking about. But yeah, it's interesting when we think about Europa and we think about the possibilities for life there. It's been very interesting to look at the discoveries in exoplanets and look at how many sort of large gas giant sized exoplanets we've been finding. And that of course is just because those are easiest to find, right? Like the bigger the planet, the easier it is to find with our techniques. So, I know that people have been talking about, we keep having announcements of, Earth-sized or Earth-like exoplanets. But in my opinion, we still haven't been able to get down to sort of the detection limit that would really give us a plausible sort of Earth-like discovery of a real exoplanet. But when we start looking at all of these giant planets, a lot of them could have moon systems. And so I think that really the discovery or the possibility of life in the outer solar system, of our solar system, it's really expanded our whole notion of the habitable zone, right? So originally, we had an idea that it's sort of like a Goldilocks story, right? Where, we have our solar system, we have Venus that's too hot, close to the sun, it's too hot. We have Mars that's too far away, it's too cold. And then Earth is just right. Earth is at sort of the place where liquid water can be stable at the surface. And so this was sort of our naive sort of beginning understanding of where life could exist, is that you had to have a world where liquid water could be stable at the surface. And I think as we've started to understand the amazing environments we could have on these water worlds, so on these worlds where, yeah, maybe liquid water is not stable at the surface, but it could be stable in a subsurface layer. As we start thinking about worlds like that, those worlds might be much more abundant, perhaps, in the solar system. And certainly they could exist as moons of these giant planets that we've found so far. So I think that it really expands our whole notion of what a habitable zone could be. And it gives us a lot more options for places where life could exist.
Because they don't just have to be in the sweet spot where it's too cold and too close to the sun and too hot.
Right.
They could be anywhere in a solar system as long as they have a planet. And they could even be around rogue planets that don't have a solar system. They're just... How many of the planets in the galaxy are rogue, starless?
Oh, I have no idea. I know that they've started discovering these. I kind of have trouble with there being life on a rogue planet. Maybe remnant life from back when it was in a solar system. But, again, the reason why we could have a liquid ocean and maybe life on Europa is that it's in this resonance. So it's in this system around Jupiter. If Europa was just floating by itself in space, there'd be nothing to tug on it. There'd be nothing to keep that water liquid. There'd be no heat source. And so
Mm.
basically over time, maybe whatever life was there could survive for a while, as you're
Mhm.
kind of throwing it out through space, but eventually there'd be no way to renew that heat. And
But
so eventually it would just freeze over and become, a boring chunk of ice, basically.
I meant if Jupiter was rogue, if Jupiter
Oh,
was
if Jupiter
floating.
was rogue.
Yeah.
Um, with a satellite system around it. I mean, maybe, right?
I don't know how that works. I just
Yeah.
I just hear
I'm
this.
thinking about in the episode of the original Star Trek where you had this asteroid that had a whole world inside it that was like a spaceship.
Mhm.
When I think of rogue planets, that's kind of what I'm thinking of, is something that really is much more technological than just kind of a chunk of rock and ice that's been ejected from a solar system and is floating around in space with no star.
Yeah, there was this theory that the reason for the Fermi paradox is because Earth is very warm, it's very close to the sun, so it has a lot of land. But most planets that have liquid water also don't have land. They have too much water, so you can't get from the water and to land because you don't have land. Does that make
Yeah, I
sense to
mean,
you? Or?
a lot of these, so before we started finding exoplanets, the theory was that any solar systems beyond the Earth would look like our solar system. And that's
Mhm.
just because, statistics of small numbers, right? We had one example. And so therefore our assumption was that everything would look like our solar system with some rocky planets and then some giant planets and nice and kind of organized. And so as we started finding these exoplanet systems, they're all totally different from what we have here on Earth. And again, part of that is just that we're still not down at the detection limit where we could find Earth-sized planets around a star that's in a similar category to our sun, right? So trying to find those is difficult. And so we're still sort of below the limit of resolution where we could find solar systems like our own. But what we have been finding is just this amazing abundance of just messy looking solar system with giant planets that are close to a sun and, tons of them. And, some of them are further out and planets around little tiny stars. And, it's just this huge abundance. And so I think that we still suffer from sort of this statistics of small numbers, right? I have a lot of respect for the people who do modeling, but basically if you have one data point, you can fit any line you want to that data point, right?
Yeah.
And so a lot of times I think that these models start with so little data and they extrapolate so much that I think you have to be careful when you try to read too much into them.
I mean, because obviously, for life to develop, you need a solar system that's very stable for a very long time. So the odds
Well,
are,
so that's what we think, right?
yeah,
One of the interesting things about the development of life on Earth is that it looks like as soon as life was possible, right? So as soon as Earth was sort of stabilized enough, it, wasn't getting bombarded like crazy anymore, and it had kind of stable environments on the surface, as soon as life could have formed, it did, right? So it's not necessarily the case that you need a stable system over billions of years before life can form, because it looks like life might have formed on Earth, billions of years ago. Certainly to develop complex life or technological life, I think that's absolutely the case, that you need that stability over time. But we still don't know how life started on Earth, right? So I think that you can't rule out having sort of an origin of life on a planet that's a much more disruptive kind of solar system. But certainly for that life to grow and evolve and become complex, then yeah.
why haven't we seen any signs of anything? No technology, no radio transmissions, nothing.
Right. And that's the question. I spent 15 years working at the SETI Institute, actually, before I came to JPL. And so that's a question we dealt with every day,
Oh,
was why haven't we found anything? And so it could just be, there's kind of two sides to this, right? So the side that I prefer, and again, this is me speaking as a human, not as a scientist, right? So sort of the non-scientific decision that the hope that I have is that the galaxy is teeming with life, and that for whatever reason, it's intentionally not contacting us. right? So this is kind of like the Star Trek view of the universe. But yeah, that basically we're too primitive, right? We're not ready. And once we're ready, once we stop killing each other and develop warp drive or whatever the criteria is that we need to become sort of an advanced civilization, that the Vulcans will be there with a welcome party. And okay, that's a science fiction story, but it's not completely implausible, right? We don't know what the universe is like, what the galaxy is like. And it's entirely plausible that one explanation for the Fermi paradox, for why we haven't found any signs of life, is that they're not ready to talk to us yet. I think that the other side of it, so in the Drake equation, there's the Drake equation is basically an estimate of, the probability of finding intelligent civilizations, intelligent sort of technological civilizations. And so there's this lifetime factor. And so, back during sort of the Cold War era, when it looked like we were about to blow ourselves up, it looked like there was this sort of that potentially there was a concern about the lifetime of intelligent civilizations, right? That maybe they have to go through this sort of very dangerous period. And, the depressing answer could be that most civilizations didn't make it through kind of this technological bottleneck. They blew each other up, and very few actually emerged into, whatever future of a more cooperative spacefaring civilization would be. There's the possibility that, right now we're sending a lot less stuff out into space than we used to, right? Because rather than just blasting out with radio signals that, radio and TV transmissions that leak off of the Earth out into space at, the speed of light, rather than doing that, most of our transmissions now are much more, from satellites pointed back down at the Earth. So we're leaking a lot less. We're giving off a lot less of these sort of unintentional signals that we gave off, say, 50 years ago. And so it's possible that we're not, that one of the reasons why we haven't detected any of these sort of unintentional signals is that the time period during which civilizations sort of let these signals leak off of their planets is very small, as has turned out to be the case here on Earth. It could be that there's intelligent civilizations that are sending out signals using some technology or wavelength that we haven't discovered yet, right? That there's some, law of physics that we haven't gotten to yet. And then there's the more depressing, right, possibilities, which is that, maybe we're one of the first. And that's a weird thing to think about. But it is possible, because if you look at the sort of, you start from the Big Bang and you look at how stars were formed. The process of nucleogenesis basically is the process by which all of the heavier elements are made. And speaking as an astronomer, basically anything heavier than like helium is a heavy element. But most of those are made by, explosions of stars, which then incorporate, and then you have more stars that form and they incorporate the heavier elements, the metals from this previous star. And so you need a couple generations of star formation and then explosion and a supernova and then a new star forming before you can get sort of metals and the higher order elements. And so it's possible, if you look at sort of the whole age of the galaxy, not the solar system, but our star is kind of like a third generation star that incorporates enough of these sort of metals, these higher order elements that came from supernovas of a previous generation of stars. It's possible that our solar system, just through pure chance, turns out to be sort of one of the first of this generation. If you look at average stellar lifetimes, the formation of our solar system, where we could have rocky metallic planets. So planets that are suitable not just for the formation of, very simple life, but complex, technological, intelligent life. This is actually a real possibility, and it's one that again, how are you going to prove it? But it's still, I think it's a possible explanation for why we haven't heard from anyone, is that maybe we're the first, right? Or one of the first, or, maybe the other ones in sort of this first generation of star systems that were able to have planets that could support life, they're spread so far apart that even though there's all these planets out there, none of them are suitable for the development of life yet, right? And that we're just unlucky. I think that's possible. But yeah, I mean, you can speculate endlessly, right? And again, in the absence of data, you have no data points that are constraining things except for, that single data point, which is that there is life on Earth. You can come up with all sorts of theories.
So you would need. I've never heard this one before. It's amazing. So I didn't know that our star was a grandchild. That it's a third generation of star. That's amazing.
I haven't taken astrophysics in a while, so it's that's the basic story. I may have some of the details wrong, but that's the idea.
It's
that
common knowledge.
Yeah.
That our star is a third generation star. That's everyone knows that in that world.
Something like that, yeah.
So you can imagine that in a couple of billion years, there's a fourth generation of stars, and you have even more complex metals, complex atoms, basically.
Right.
And then you'll have a better universe to have life in.
That's quite possible.
And that's why Star Wars starts with, no, that's a long time ago. So that's
right.
Really
it's in
weird.
The wrong direction. Yeah.
No, that doesn't make sense. Star Wars is wrong. How could it? How could it be?
Star Wars is really it's a fantasy, right?
Yes.
Star Trek is science fiction.
Yeah, I hear
Star
you're
Wars
tricky.
is really fantasy, just set in space. I love them both, right? But yeah, one of them is set in a universe that has rules like ours, and one of them is not.
Do you have any ideas for how life on Europa, life on Titan, methane-based life, what it could look like if it would be DNA based or based on, I don't know, fluoride or something?
Yeah, I mean, that's a great question. There's reasons why carbon is sort of the building block of life. And again, this is life as we know it. And that's because carbon has basically certain chemical properties that mean that it's the most sort of versatile and adaptable element to have life based on. And so carbon is kind of the backbone of our whole DNA-based life system here on Earth. That's not to say that you couldn't have a different configuration somewhere else. And sorry to drag Star Trek back in, but it's really a great place to explore some of these ideas, right? And so there's a Star Trek episode where they encounter the Horta, which is this silicon-based creature that doesn't show up as life on any of their scanners because their scanners are all made to detect life as we know it. That's carbon-based life. And so the silicon-based life form, it turns out it is actually intelligent life. And what's really interesting is that, I don't know whether the Star Trek writers were just, prescient or whether they were just lucky, but basically, if you don't have life based on carbon, it turns out silicon is kind of the next best thing to base life off of. So for some reason, you couldn't have carbon-based life. Silicon-based life would probably be the next thing that you could build up the structures of life from, sort of a DNA-like system.
Okay.
But yeah, it certainly is possible that there's life out there that takes forms that we just can't even imagine, that are so different from what we would even be able to identify as life, based on our experience. And this is really where, the bounds between science and science fiction are so fascinating, right? Is that when we search for life, it's life as we know it. It's based on a certain set of assumptions that we've made about what life would look like, but we could be wrong. We could be totally wrong. There could be some totally different form of life out there. Yeah, maybe on Titan you could have life that's based on a totally different set of chemicals. It's possible.
I think Amanda Hendricks suggested methane-based life. I really would love to have Amanda here. I don't know if you've met her.
Yeah, she's great.
Yeah, I guess I should go. How would silicon-based life look? Would it look the same as here, or would it just look different on a very basic way so that you would notice it immediately? As a cartoonist, I need to know this.
Well, as we know from Star Trek, it looks like this giant kind of shag rug with these little, fringes hanging off on the bottom.
Ooh. Do you have, are any scientists working professionally or systematically on developing or explore, or is this the area of writers, cartoonists, movie makers?
I mean, it's really both. The problem is that once you start speculating about life based on a different set of elements, your starting point is just so different from, say, carbon-based life, that it's really a question of, where do you go from there? So for example, there was this potential discovery a few years back about where somebody thought that there could be life based on arsenic.
Yeah.
So replacing, so it turned out that those results were actually not correct, which was, kind of disappointing in a way, but also kind of, it leaned us back toward our more traditional understandings of what life needs to be based on. But even in that case, honestly, a microbe is kind of a microbe. And so I think that when you're talking about single-celled organisms, again, my guess, my hunch based on zero data at all would be that microscopic life that was based on, silicon or carbon or whatever, it probably wouldn't look that fundamentally different. However, when you start trying to build up sort of macroscopic life that's based on a completely different set of fundamental chemistry, that's really a question. So
Yeah.
I don't know. I think that, that's where the imagination of artists really needs to come in.
Who's the best in the world to ask if I want to ask a scientist about that?
I'd have to think about that.
Is there any reason at all for humans to go to Europa? That's pretty pointless.
Well, I mean, I think that eventually, again, to bring in science fiction, if, I'm a big fan of The Expanse. And
Yeah.
so that's basically a realistic story that's set in a time when we've colonized the solar system. I think that once we've expanded beyond the Earth and once we've explored and really, settled on these other worlds in the solar system, then yeah, I think that there might be very good reasons to have humans living on Europa. Probably it wouldn't be on the surface unless we discover some kind of, amazing shielding material that would let us survive there given that radiation. But certainly in the subsurface, down in the ice layer, there's plenty of water, right? So that's one resource that would be useful for humans.
Oh, you think the water would be the valuable thing there, or just the science? I mean, just the risk of polluting Europa would be massive. So I feel like the loss is huge.
Yeah, I mean that certainly is a concern. There's something called planetary protection, which basically is a mandate from NASA that you don't want to contaminate the other planets in the solar system in the act of exploring them.
Yeah.
And certainly places like Europa, it's a special place that could have life, and we have to be extra careful about what we do there.
How
So
on
yeah,
earth?
so any future colonization would have to take place after we've decided, okay, there actually is no life on Europa. It's okay to go and breathe all over it and drink the water.
How would you do the landing with the Europa lander? How well can you clean a lander like that?
You can actually clean it very well. We can sterilize it. And fortunately, the radiation around Europa that's so bad for the spacecraft also is very bad for any microbes. And so the radiation actually helps sterilize it. So we can take advantage of some of that. But yeah, one of the possibilities, so we have that radiation protected vault where the instruments are, but that means that the radiation isn't going to get in there and sterilize it as well. And so we've looked into various ways of making sure that nothing survives there. And one possibility is actually to blow it up seriously, to sort of detonate the inside of the vault so that you kill off at the end of the mission right before you're like, okay, my spacecraft's about to die, the radiation's built up too much. You set off kind of an explosion inside the vault that would kill off anything that was still in there. We're hoping we don't have to do that because that's kind of a crazy thing to have on board your spacecraft.
Yeah.
But that's kind of one end number of possibilities we've even been looking at because yeah, we have to take this very, very seriously.
Of course. Thank you so much, Cynthia.
Sure. Glad to chat here.
This podcast is sponsored by my Patreon, patreon.com/runde. Just put some money there if you want to help me make more stuff like this and more stuff like my sci-fi comic, Cosmic Bullet, which will be somewhat based on the research that I do when interviewing these amazing people.